We're on 4 o'clock, so I'm going to make a start. Again, welcome everybody. Great to have you here. And we've got a great session with Trevor Clements and Simon Green. Their bios are in the chat if you want to get the lowdown on their history. Once again, please put your LinkedIn details in the chat and I can connect with you later. And also the Q&A button you'll see at the bottom of your screen. Please put any questions in there during the session and we'll get through those at the end. So without further ado, I'll hand over to Trevor, who's going to do a short introduction.
Thank you, Rach. Yeah, just see Ghana. We've got somebody from Ghana, so I think that nobody's going to pick that. So fantastic. Anyway, must crack on because there's a lot to fit in. And as I say, I'm just the warm-up act and you'll all be anxious to hear from the main event, Simon. The Future Home Standard and Approved Document L. So where are we now before we go on to what's happening in the future? So we should be getting used to the interim Part L and F standards that came in recently and we've been using since June last year on all projects. We covered that in detail in a previous seminar. If you missed that, there's a recording available on the HBC website. So I wonder how that's bedding in for all you building control people in the audience. We've got these new provisions such as the need to check mid-build photographs of the key elements on completion. I wonder if that's being done effectively at the moment. How about that new requirement for analysing whether retrospective work on properties might adversely affect ventilation and air quality? When I saw that coming, I thought, how's that going to pan out? I'd be interested to hear, are we on to that? And that's just two of the many new requirements that we've all got to get our head round. And it'd be nice to know that we're going to apply them effectively and also, more importantly, in a consistent way around the country. And to do that, especially with the energy requirements, building control need a broader knowledge. We need to know more about the latest heating and ventilating technology, how systems are designed and commissioned. And not just us, it's also the installers of these systems. They've got to try and wean themselves off gas boilers and onto low carbon technology. So let's hope we're all prepared for the changes to come so that we can harness the maximum benefit potential in terms of carbon output and in efficiency in the future. Rach, what symbol do you want? I'll just go that for a new slide, and there we are. Does that look familiar to you? Well, if you saw the previous presentation, it would. It's the implementation timeline towards the Future Homes Standard for 2025. So we're now working with the interim version, as I said, of ADL, and that aims for 31% less carbon than the previous standard. But now we need to move towards the 75 to 80% target set for 2025. In other words, full fat Future Home Standard. Bit of a tongue twister, but managed it. So we're well down that road, as you can see from the big red arrow, into the penultimate phase. And much work has been going on behind the scenes by government and the new building safety regulator to present the FHS consultation document that was published last December, along with a draft amended version of a new approved document L. So later this year, we should see the publication of the final version of that ADL, which will come into force in 2025, and there will be a 12-month implementation of that, a transitional period, and we're waiting to hear on what the details of that will be. No doubt we'll do another webinar to give you the full details of the final version. Rach. So with the few minutes I've got left, before I hand over, I'll briskly cover some of the contents of the consultation, hopefully without gabbling. Rewording of the requirement L1. It's going to be called Conservation of Fuel and Power and Minimisation of Greenhouse Gas Emissions, just focusing in on what we're trying to achieve. We're going to get a new home energy model, the HEM, replacing the standard assessment procedure. So HEM replaces SAP, and this will be the approved methodology to demonstrate Part L compliance for new dwellings. And as with SAP, it sets targets for the three metrics that most of you are familiar with, I'm sure, which are carbon emission rates, primary energy consumption, and fabric efficiency. It's probably going to be refined in many ways. One of them will be that it will use local weather temperatures rather than national averages. It will use separately calculated thermal bridging values, the Y values, rather than accept defaults as SAP does currently. And also it's going to run a far more detailed simulation of energy use, a sort of an hour by hour, or I'm not sure it's hour by hour or half hour by half hour segments. So it should all improve the accuracy of the predictions for energy performance. All until, of course, somebody hands a key over to a human being who then enters that property and takes control, and then it's all bets are off. But we can't do much about that, can we? And as with the SAP, of course, the HEM will form part of the BREL report, the Building Regulations England Part L, that the developer has to hand over to ourselves in building control and the energy consultant at the end of the job, with all those photographs, etc., and that calculation. So, what about fossil fuels? Because of course, we're all going to wonder what's going to happen with fossil fuel boilers. Well, they won't meet standards for new homes. I think that's going to be absolutely certain. It's confirmed in the draft approved document, which sets minimum emission factors and primary energy factors for fuels. Gas and oil just can't hit those marks, so they won't be incorporated, and that neither will solid fuels and things like hydrogen-ready boilers, as they're being called, because they will also burn natural gas. They won't hit the marks either. So it's all steering towards heat pumps. We've got two options being considered in the HEM as the notional home for those calculations. What's the notional home? Well, that's the design specification that's put forward as achieving a benchmark performance that has to be achieved by all dwellings to get that 75% minimum carbon saving. So both those options that are being considered use air source heat pumps for heating and hot water. Option one is the most cost and carbon efficient to run, but it also costs a bit more to build. Option two costs less to install, but the running costs are slightly higher, obviously not as high as current properties, and it's also slightly less carbon efficient. We've also got two notional home model options on the table for homes that are linked to heating networks. Rach. Solar photovoltaics, what's going to happen with those? Well, it's a little bit uncertain. Photovoltaics may save on bills, but the consultation is more concerned with carbon emissions. And of course, they bring less benefit in carbon terms if the grid becomes decarbonised. That said, as we know, home generation and storage of electrical energy can contribute to that decarbonisation nationally. So we'll have to wait and see what they bolt into the new standards. I do notice that one of those notional standards I mentioned doesn't have any photovoltaics in that dwelling model. So that's interesting to see. In terms of fabric efficiency, don't expect much change there. The maximum U values for roof, walls, floors, windows, etc., all seem to be unchanged in both the notional models. As we all realise, it's a law of diminishing returns when it comes to thickening insulation and trying to increase U values. So the already held standards will just be maintained. We may see a slightly lower air tightness target on those notional models, going to 4 meters cubed from 5 meters cubed per meter squared at 50 pascals pressure differential. And that will tend to promote the use of mechanical ventilation because natural ventilation just isn't compatible with that level of air tightness. What else we got? Tweaks to building energy surface to building services, energy efficiencies, things like mechanical extraction and lighting efficiency, and also increased insulation for hot water vessels. Thank you, Rach. Moving on, changes of use, and by that I mean things like conversions to form dwellings. We can expect higher energy efficiency standards for these, and possibly a new requirement for SAP calculations and BREL reports for this type of work. So you're considering the whole building energy performance. In order to try and further address the performance gap between design expectations and real life energy efficiency, the government is considering introducing energy performance testing for new homes, which I think is an interesting one and a sensible one, don't you? And how do they do that? Well, possibly by using smart energy meters, just to see real life how much energy a building is used with a temperature difference given. So we'll, as I say, I think that sounds sensible. We'll see how that pans out. There's going to be a lot more detailed guidance on commissioning of systems to get the best out of them. Heating, ventilation, home battery systems, all detailed advice there. Of course, you can lead a horse to water, but we'll see if that horse drinks. And who's going to be looking over their shoulders, I wonder? Is it going to be building control? And if it is, well, then we do, as I said earlier, we need to swat up on our commissioning and of low energy systems, because if you're like me, you know, there's scope to increase our knowledge, which we will be doing in a moment, of course. Finally, promotion of smart meters, not necessarily mandatory, I don't think, but if you've got a smart meter, obviously, in terms of the cost of your energy, you can exploit the lower off-peak tariffs that a lot of companies are making available now. And if you bolt on some energy storage, then you can exploit it even more, but we'll see how that pans out. And finally, repeal of regulations 25A and 25B. These are the regulations that said applicants must consider high efficiency alternative systems, and also that buildings must be nearly zero energy. Well, we've moved on from that. They're now redundant, so they're being scrapped. Rach, crikey, I'm well over time, aren't I? And I've really been gabbling. Little change on existing dwellings. No change to U-value developments. You'll still be able to replace your gas boiler with another gas boiler of the same or better efficiency. And if you change the fuel, well, as long as it's the same or better primary energy efficiency, then that's fine. You can do that. So not a lot of changes there. Next slide. What predictions for the future? Well, am I able to look into a crystal ball and look for enlightenment? To be honest, no. I look at all the conflicting media on the subject and I find it very confusing. Heat pumps or hydrogen? I don't know. Next slide. And thanks for the CGI on that one, Rach. It's a very good job. Thank you. And there you are. There's some of those headlines, pro and con. So either hydrogen could be our saviour, or forget hydrogen. It's just not an answer. Next slide, Rach. And a credible comment there from an industry source, David Cowdery, Director of External Affairs at Microgeneration Certification Scheme, saying it's hydrogen, forget it, it's a costly chimera. The NIC is saying it's not a solution, the government's own advisor, in other words, and that we should ignore the false promises and harness the tested efficient heat pumps at huge scale. Finally, last slide. Oh, we've bumped a slide there, but there you go. Oh, I think we've got our slides out of order. Finally. So I'm sorry, Rach and I have got our slides. That's my fault because I swapped them round. But there's David's comment, which I just got on about. And I know everybody loves these glitches. And Rachel, if we go to that one bit that we had before now. That's it. So just to show the conflict, the article on the left in the Telegraph, and that's saying heat pumps are poorly suited to British homes, and the government's relentless drive to install them will cause uproar across the country. Energy leaders have warned. Well, on the right there, you've got an energy leader. That's the Energy Saving Trust website saying, well, flats, terraced houses, heat pumps are suitable for all property types. So they're muddy waters, as you can see. And I think there's a lot of commercial interests that are distorting the picture there. So even with that trusty crystal ball, I can't offer you a properly informed opinion, and uninformed opinions, as we know, are worthless. However, I do know a man who is well informed, and let me ask him to take the floor. Simon Green of Green Building Design, based in Hertford.
Well, thank you very much, Trevor. That's an interesting topic and interlude to what we're going to talk about. Dominantly, we want to explore new technologies and how they can go forward with replacing domestic heating. For my penny's worth, just on your last slide there, if your building is heated at the moment, heat pumps will work and they will heat it. If you drive your car to London and you use a Mini, you'll use less fuel than if you drive an old Range Rover to London. Both will get you to London. One will use more energy than the other, and that's exactly the same with heat pumps. You know, any heat pump can heat any building in any country in any climate. It may cost you more energy, but it was costing you more energy in your fossil fuel. So in that answer, you know, anything will work if it's designed properly. You know, back to the slides. I'm Simon Green. We are low energy consultants, and you know, dominantly now really specialising in with phone calls almost on a daily basis on, you know, can we convert our house to low energy, or can we, you know, try and reduce carbon? What can I do to get my energy bills down? And now with this race to zero well underway, you know, now I think is really the time for every individual and businesses to start addressing this issue and start to go green. So hopefully I'm going to answer some of this today as what is green technology? How does it save costs? What are some of the potential challenges with installing green technology in our homes and in our businesses? So we've got the agenda there. So I'm going to touch on gas boilers, touch on green technology, heat pumps. What are they? What's a ground source heat pump? What's an air source heat pump? Air source heat pumps probably are more common than the ground, and then, you know, look at versing them against our lovely gas boilers. Moving on to the challenges and benefits. How we can reduce costs, issues with space and noise, changing your mindsets, and then some case studies with a little look at the future, time permitting. So if we go to the next slide, please. So I assume everybody on the call knows what a gas boiler is. In my view, as an environmental engineer, they are fantastic things. They are small. They are cheap to install. They're certainly cheap to run. And relatively efficiency is 98% for modern ones, 80% for older ones. They produce hot water at a good temperature of 80 degrees. Combination boilers, probably even better, have a larger internal heat exchanger, so they're able to provide instantaneous hot water from 10 degrees to 50. For washing, you know, standard boilers have exactly the same, but they would then obviously transfer that heat to a cylinder via a coil, and you have a tank of hot water. So the poor old heat pump's got a lot to match up to, because we have had it too good for too long. Next slide, please. So what is green technology? Well, you'd obviously think the wind, wave, tidal, solar. You know, those are obviously key ones that come to mind. But next slide, please. You know, if you look at you know, what actually is constituting green technology, broadly speaking, the definition would be any technology that reduces energy consumption whilst providing a similar result, particularly where your source of heating fuel is from fossil fuels. So significant savings can be made by improving insulation values. May seem obvious, but you'd be surprised at what that can save, and that can clearly be modelled quite accurately on modern software now. Now, whilst it may seem an obvious statement, we need to be real careful in Britain now about our mild summers and all this insulation and the sealing up of them, that we then don't end up with buildings that overheat regularly in the summer. And we know we are finding a lot of new flats now don't cost a lot of money to heat, but are a real difficult thing to cool down in the summer. And we really need to now model much more than we used to summertime over temperatures and ensuring there's enough ventilation in the summer to through ventilate those buildings. So, I mean, if you are looking at natural ventilation for your building, you really do need to then consider the environment. As it, I've seen on models before where, they said if your windows are fully open all day and all night, then it won't overheat. But that may not be appropriate with noise pollution or with if it's next to a roadway or something that's going to get pollution. And again, nighttime cooling is needed to keep your house cool. Well, how does that work with security where you can't really be safe to leave the windows open all night? So, with modern houses now, we've really, really got to consider that summertime cooling. So probably, we've talked about heat pumps, and the most common type of efficiency would be to focus away from the boiler and go on to a heat pump. So if we go to the next slide, please. So first, just go to the next. First, really, there are two types of heat pumps. There are number one, which is the ground source heat pump, and then number two, there is the air source heat pump. So this picture here is showing how a ground source heat pump would be installed. Now, on the ground source heat pumps, there are dominantly two types. One involving trenches and a slinky coil, as per that picture, and the other would be with boreholes, typically driving down 100 meters. And each borehole can probably give you 4 or 5 kilowatts, depending on the geography build of your ground. And these trenches, they're typically 1.5 meters deep, 1.5 meters wide, with the pipework slung on the bottom, like the picture shows. And you get about 3 or 4 kilowatts per 10 meters. So for a modern house, maybe needing 25 kilowatts, you may end up needing a trench that's about 260 meters long, or you may need 5 or 6 boreholes, which need to be 5 meters spaced apart. So you can see really that ground source heat pump is pretty limited to lucky people with very, very large gardens, or if the building is being piled and it's brand new, there's opportunities, maybe you can use the piles. Whilst manufacturers will always claim a ground source heat pump is a lot more efficient than air source heat pumps, and that seems to be the main seller, as manufacturers claiming that. I'm personally not as convinced. There's a lot of pipework for you to run water all the way through those coils and bring that hot energy back. The main thrust of their argument seems to be is the ground temperature at that depth is between 3 and 10 degrees, doesn't vary greatly. And if you compare that to an air source heat pump taking its heat from the air, clearly it works harder in the winter. Our experience with modern houses now is that hot water load is often much, much larger than the heat pumps. And clearly there are many, many days in our country when the outside temperature is above 10 degrees. And in those sorts of scenarios, I would question whether the ground source is actually greener or more efficient. We go on to the next slide, please. So let me explain really a bit more about air source heat pumps. Basically, they are a very energy efficient machine. They can heat and cool our buildings, and they can provide hot water. They use a compressor and a refrigerant cycle, and electrical energy goes in, and the only thing that comes out of them in waste is condensate water. So obviously, the government wants our electrical grid to become greener and be less reliant on fossil fuels. And therefore, if we only burn electrically driven machines to heat and cool our buildings, there's going to be less CO2 put out. And if you could get a grid that was completely green, therefore we would be in our race to zero and be carbon neutral by 2050 as is required. Now, heat pumps basically use the latent air that's in the air, or latent heat that's in the ground. And using a refrigerant cycle of high and low pressure through expansion and compression, they're able to extract heat from the air, which is then used to heat our buildings. An air source heat pump then absorbs heat from the outside air into the refrigerant, even at low temperatures below freezing, and indeed special ones can work easily at -15. So all of these comments that our country's too cold or Scotland's too cold is rubbish. The biggest provider or seller, of heat pumps is Norway, where their winters are much, much more extreme than ours. So using electricity, the pump compresses the liquid, which increases its temperature to extract from the air, and then it condenses it back in the house, back into a liquid, which then would release its heat into the building. So it's quite a simple policy. Then that heat is either sent to your radiators or underfloor heating, or it can be sent to the hot water cylinder. Next slide, please. So typically, for every electrical kilowatt of energy put into a heat pump, it can produce, typically in a heating mode, 3 to 4 kilowatts of heat. So let's think about that. That's pretty magical, isn't it, really? 1 kilowatt in, 3 or 4 kilowatts to our space. Compare that back to our lovely gas boiler, where our particularly 80 to 98% efficiency. You can start understanding why people are talking about the carbon saving, the CO2 saving. So, clearly a heat pump is used in somewhere between 1/3 and 25% from a carbon point of view. So efficiencies are critical with air source heat pumps. Now, as engineers, we love our codes. So you will often see a code of COP. Now, the COP for heating only stands for a coefficient of performance. And what that does is it looks at a very, very specific set of engineering conditions, the exact temperature of our outside air, exact temperature of our water or air that we're going to heat up internally. And on that number, there was all those criteria with exact machine, it will give you a number. And that is the efficiency of the machine at that type of condition. Now, that's not really very helpful because obviously the outside temperature can vary an awful lot. And with some weather compensating controls, we can vary the inside temperature. So what the manufacturers have done is they've calculated how many hours on a typical year it is -5, -3, -2, -1, blah, blah, blah. And overall, they've worked out all the efficiencies at those different temperatures and different conditions to give you a SCOP. SCOP stands for seasonal coefficient of performance. So really, as engineers, and if you're trying to make a judgment to buy one of these things at home, that's the key ingredient you need to look for selection of those heat pumps, because the seasonal efficiency really gives you an overall number, I'd say 3.9, 4.5 of what the machine efficiency is typically going to do over a heating season. Now, I've touched on temperatures. I can't do much about the outside temperature, but I can try and do more about the inside temperature. So fundamentally, the lower the inside temperature we can allow for heating means basically the less hard the heat pump needs to work to extract the latent heat, which kind of means it's more efficient. So in the words, the hotter the output temperature, the less heat efficient the heat pump is. So really your design then starts to become into a crossroads. If we're building a brand new house, we can put new radiators in and we can size those radiators down to as low as 40 degrees. And we do some examples on efficiencies there in a minute. But if you are trying to do a like-for-like replacement, and I've got an example on that to come in a bit, where you may have to work out that the temperature of the radiators need to be 70 degrees. When it's -5 outside, that can drop the COP at that specific moment down to 2.2, compared to an average one where you could be at 4. So at that particular kind of period, it's costing you twice as much to run that heat pump as if you had allowed the higher temperatures. But we'll talk about that in a minute with some more examples. So if we go to the next slide. So I just want to do a quick ground source, the air source sort of criteria. I have been accused in the past of being a little bit too pro on air source and not as positive about ground source. So, the manufacturers will report that ground source is more efficient than an air source heat pump, where they would typically achieve COPs of 3.5 to 3.8 with a 50-degree temperature, feeding their underfloor heating, compared, say, to an air source heat pump at -4, -5, where it may be down as low as 3 to 1. So in that scenario, at 50 degrees, clearly an air source heat pump is not as efficient. The ground source really, the heat exchanger outside should last a lot longer because it's pipe braid in the ground. So provided you don't dig it up or put tree roots through it, it should in theory last 25 years. Clearly, there's no external noise with that plant, and we don't really need any external space. We can bring all that pipe work back from those slinkies underground through the foundations into the heat exchanger in the house. Compared then to the advantages with the air source heat pump, clearly it's much, much cheaper to install. We don't need all those groundworks, all those holes to be drilled. Typically, it's much quicker to install. It does need a slightly smaller space externally in terms of we need to find a box for it. And it's obviously much easier to install into an existing building. We need to find a location for it, screw to the wall or down in a little remote area. So hopefully that tries to give the differences between the two. And then if we go to the next slide, please. So here we're now going to then talk about the comparisons of an air source pump v a modern gas boiler. So I've got another code for you, unfortunately. Air source heat pumps, depending on what they are, they can heat and they can also cool in the summer. Now, they're much, much better at cooling your buildings than heating it. And so for that, the manufacturers have another code called an SEER. So it's really important that if you see the SEER, you don't get that confused with the COPs. So in its cooling mode, we can get between 7 and 10 to 1. Again, thinking about that, 1 kilowatt in, 10 kilowatts of cooling, that's pretty amazing really, isn't it? Which is exactly how your fridge works. So your fridge is very, very efficient at home and is a mini heat pump all on its own. So in heating mode, seasonal efficiencies, usually are around about 3.9. So again, thinking about that, 1 kilowatt in, 3.9 kilowatts to the space. It's quite difficult to get exact COPs from the manufacturers, as they only really want to talk about the seasonal. But I've managed from Mitsubishi to get on one of their machines some figures which are useful to look at. So when it was -7 outside, which again isn't very often, this particular machine dropped down to 3 to 1. When it rose to -3, it was 3.4. At 0, it was 3.7. At 1 degree is 3.9. And at plus 25, it was running at 5. So again, you think about your hot water loads, which often are more than your heating. If you are starting to achieve 5 to 1, maybe 6 to 1 in the real summer, you can see how much cheaper this machine is to run than a gas boiler. So the graph there we've got there up on your slide is trying to show how much energy input is being used and saved by a heat pump compared to the modern gas condensing boiler, say with a 94% efficiency. So to recap, what you're seeing there is obviously 3 to 1 heating. And obviously the yellow is showing how many kilowatt hours of air source heat pumps. And the gas is obviously at nearly 103 or 4%. So this next slide we've got is now going to talk about the cost. Now, this is the most important thing we've got to be so careful of is if I spoke to you all 4 or 5 years ago and said, what's the gas bill? Probably most people wouldn't really know. If I said, what's the electric bill? They probably would know, even though the gas is doing all the heavy lifting. And that's dominantly because typically gas costs about 1/3 of electrical energy. Now, this slide was taken in October in 22 during the height peak of uncertainty about gas prices following the war and COVID and everything else, and all the marketeering that could go in to maximize the profits for energy companies they could probably get away with. Now, the cost to run my office at the time is what this slide is based upon. And we were paying 60.5 pence for a kilowatt hour for electricity, probably about half that now. And we were paying 20.2p a kilowatt hour for gas. Again, probably slightly less than half of that now. But it doesn't matter, the maths is the same, the gap's the same. So that second graph now is looking at the cost to provide 100 kilowatt hours of heating on the green, which doing the maths, 38.5 CPO times 60 times 100 is 17.28 pounds. And then the gas boiler, 100 kilowatt hours times 20.2 times So the 9 efficiency comes out at £20.82. So you can see that at that efficiency, it's still cheaper to run air source heat pump. And obviously, we can calculate that saving over a year of a typical heating season and add some hot water to that and start showing you then, how much a year it's saving, and then possibly leading back to a payback, or not, as the case may be. So in this instance, then you can see it is cheaper to run our heat pump than a gas boiler. But it also shows that we've got to ensure that the heat pumps are running in the efficient zones. So if we go to the next slide, please. This hopefully starts to show how important the efficiencies are. So the graph on the left then is now basically an air source heat pump running at 40-degree hot water temperature, which is pretty low, and that could mean that the radiators need to be on for much, much longer periods of time to warm your house up, because there's not that much transfer of heat, but there still is a transfer of heat. It's just going to take longer to heat your spaces up. Again, if we use the costs that we had before from my office in October 2022, we can now start seeing that the cost with a COP of 4.5 at that condition drops down to 13.4 pence compared to the 20 pence that we had before. So in these instances, you're starting to see some real savings of running an air source heat pump in these extreme lower temperature conditions. And obviously remember, we're also using a lot less carbon as well as being cheaper to run. So hopefully it's a win-win. So if we move on to the next slide, this will start now to talk about the challenges with this super duper efficient machine. Cost, I think, is probably the most key one. But they are a lot more expensive than a gas boiler, ignoring all the cost possibly of changing the radiators. So you really need to look for grants. At the moment there is a grant, I think it's until March, which will give you £3,500 towards it, which will help tremendously. Space is probably our next biggest challenge. If you think I've got a small flat with a combi boiler, which will have that combi boiler stuck in the kitchen somewhere on an external wall with a balanced flue that provides me limitless hot water and heats my house. I now need to find a large area for a heat exchanger to go internally. And then next to it, with all air source heating, I need to then find a tank to provide you enough hot water. So at the very least, I need then a double cupboard somewhere, which may be a big impact on a small flat at 64 square meters, providing I can find a space externally for your condenser. So space is a real problem. The outside condenser, I need to find a space for that. Now, condensers do make some noise. They will be subject to planning conditions. And, but they need to be correctly designed and sized so that, we can make sure they're not an issue. Again, I wouldn't advise putting them outside bedroom windows. Certainly in the summer, if you're going to run them, then you will hear them. But probably not much more noise than you will have in your boiler. The boiler will make noise and will discharge through the flue. And our biggest next challenge, I think, is probably people's mindsets. Trevor's already shown you some articles about heat pumps don't work. They cost a lot of money. And they do. Electrical energy is more than gas. So we need to really, really ensure your heat pump is, one, properly designed, properly installed with qualified people. And our construction industry is still learning how to put these in. And all of our gas-fired plumbers that have been doing it for 20 years have got a lot to learn. The mindset also needs to be set. They need to be commissioned and set up properly, and you as users need to know how to use them. I often go to places where they find that the thing has cost a lot more to heat, and I find the time clock has been set to provide the hot water at 5 a.m. And so the heat pump is working really, really hard when it's cold outside to heat all that hot water up, and it's trying to work really, really hard to heat up the house. The best time to heat your hot water is in the afternoon, when the outside temperature is at its highest. So your machine is going to work at its most efficient. If that can be coupled with some PV on the roof, and I would be endorsing that every house should have PV on the roof, regardless of what the new planning regulations are starting to allude to, all of that hot water then can be heated for free in the afternoon. So you can't get better than free low carbon hot water. And again, if that tank size for a whole day's use, then that's all you need to do. All your hot water is served in the afternoon. There is a slight difference on mindset changing, that if people can go onto economy 7 type meters. Now, whilst my low carbon heat pump will work much, much harder in the afternoon, sorry, I beg your pardon, work much, much harder in the night because it's running at a colder temperature. But if it's running at half price electricity, I might be using slightly more carbon, but it may cost you a lot less to run. So there is, this change of thought where at the moment, Octopus Energy will offer you these Comedy 7 tariffs, and maybe, with some maths, that is maybe the time to change over the thinking on that. But we have to remember, that whilst electrical energy is more expensive, we are at incredible times where energy is costing between 2.5 and 4 times more than it did 4 years ago. And, it's really important, if any engineers are on this call, that you do those paybacks and you really look at how much energy it's going to cost to run that heat pump in a year, to ensure that client starts really understanding what their heat pumps are going to cost. An old engineer said to me when I was training many years ago, all this low energy nonsense is rubbish. If you want to spend less, use less. And I've kind of taken that back a step, and I've got some ideas in a minute on how you should really be thinking about how we actually use less energy. We've all been a bit guilty, certainly people like me and Trevor, of wasted energy, and gas has been too cheap for us for too long, and we've had our houses heated, virtually without anybody noticing, and time is starting to change. So next slide, please. So really, just to have a little recap before I go into my examples. Most green energy has higher upfront capital costs compared to standard technology. Ideally, costs are being paid back over time by saving energy, and consequently the reduction in energy bills. Paybacks can vary from as little as 18 months over to 20 years. And in some cases, it doesn't actually pay back at all, but there are grants there to assist, or we have to accept that low carbon solutions are what we're going to go to do. Manufacturers will quote you a COP, but more importantly, you need to find out what the SCOP is, seasonal heat efficiency, because that kind of gives you a marker of how it is to be the cost to run it over heating season. Don't get that confused with the SEER, because that's the cooling ratio, which is much better. We need to really consider what temperature we're going to run our radiators at, because the colder the radiators, the more efficient it will be, but then that may mean you've got disruption in the house to replace the radiators that are in there. Another consideration then, obviously, is the size of the plant, and where we're going to put it, and is it going to be a problem with noise? If any architects on the call, please do not think about stuffing these air source heat pumps down the north-facing alleyway, where then you box it with heavy timber fences because you don't like the look of them. Air source heat pumps are like flowers. They need space, they need air, and they need sunlight to shine for you and work much more efficiently. If you stuff them down the north elevation and you put a fence all around it, they will not work properly. They will cost you more to run, and they will be freezing up much more. And again, as we talked about, these heating products do need some noise when they're outside. So we do need to look about carefully ensuring they comply with planning regulations. Maybe need to have adjustable feet on there with anti-vibration feet, and maybe in extreme cases a small acoustic louver. But all of these things can be designed in and comply then with planning and concerns with people that are putting those in their gardens. Next slide, please. So again, whilst the upfront costs can be more, with the rise in cost in fuel, that should help with paybacks. A lot of factors do come into play when we're going to size your air source heat pump for your domestic property, and that will include how well it's insulated, going back to our first talk about the car. If you've got an old 1950s drafty farmhouse, I can definitely heat it with air source heat pumps, but it's going to cost you more to run. So looking at insulation, looking at glazing, and then another really big demand is the hot water load. I have a client, which we'll talk about in a minute, that wants big, heavy baths every day and complains about the water bill. Baths use a lot more water. So, if you want to consider reducing your bills, then let's reduce our hot water. But again, if you have a high hot water demand, then I need a hot air source heat pump that will be sized for that. And then our final really point about air source heat pumps is the temperatures. If we're going to put new underfloor heating in, perfect, at 40, 50 degrees, or put very large radiators in at 40 degrees, they'll be more efficient. But if I'm limited on what I can do with the radiators and they've still got to stay the same because you don't want disruption in the house, they will be at higher temperatures, but will make the thing more efficient and your bills will be higher. There's no magic to it. So the main problem for existing housing, is this high temperature problem. And then what do we do about the existing radiators? Do we swap them out? Do we put more radiators in? And I think really the key question is get somebody that's competent to do the maths for you. Find out how much it's going to cost to change your radiators, and then really understand what the additional costs are going to be for running those air source heat pumps at the high temperature. High temperature air source heat pumps aren't magic. They have exactly the same temperature as low temperatures. The low temperature ones raise it from whatever your temperature is to 50 degrees. And then there's a immersion heater that will raise it from 50 to 70 degrees. And that temperature, that rise in temperature is purely 1-to-1. So 1 kilowatt in, 1 kilowatt out. So there's no carbon saving there. And that's why the efficiency drops down. So to run on to a couple of examples I've got here. Example 1 is a new house. Heating only. The underfloor heating is going up sort of 40, 50 degrees. A single large tank being stored all day. There is a little immersion heater in there to top it up to 60 degrees to get rid of Legionella. And on that particular machine, the COP was running at about 4.8 to 5.1. So 5.1, remember that 5, it's easy to remember. Example 2 we had here, an existing house, which we did all the maths on. The existing gas boilers were running at 80 degrees temperature with a return of 60. Hot water was stored at 65 degrees, which we also had to do, so otherwise you wouldn't have enough hot water. So to avoid adding any more radiators or replacing the existing ones with larger ones, to make up for that lower temperatures, we had a high temperature air source heat pump installed, which was actually Daikin Alpha Thermo 3, if you're familiar with that product. And that brought the SCOP down to about 3.58.
Simon, I'm going to interrupt you because I'm not sure if we're on the right slide.
Okay, we're one ahead. We're one ahead, but I'm just about to change over.
It happens to the best of us. Don't worry about it.
Oh no, go back to slide 15. So that difference between example 1 and example 2 means example 2 has 40% extra running costs.
I don't think we saw those examples.
Okay, not to worry. If we go to slide 16, which was the one with the door, so you go back to, or come forward. Slide 16.
I don't know if I'm going forwards or backwards.
Okay, well, don't worry. The slides aren't as exciting as Trevor's were. So
so much.
Another big. How can we reduce costs? Is allow the temperature of your house to drop. Reduce hot water loads. We've talked about that. Now, I made some calculations up about boiling kettles, for example. My wife always fills the kettle up with 2 litres, boils it up, and serves out 2 cups of tea. Boiling a kettle in our house costs 21 pence on our digital meter. If you only filled that kettle to 25%, you can reduce that cost down to 5.3 pence. 15 pence, not much, I hear you cry. How many kettles of water do you do a year? Cooking food from frozen, increases cooking times by 20 to 30%. Ovens run typically between £2.13 and about £3.60 an hour to run. Do the maths yourselves, £1 to cook that pizza. Showers use about half the hot water load of baths. LED lighting with controls, it's a new way to go. We've done some modelling on a new 4-bedroom house with gas at 20 pence a kilowatt hour. And now heating that house all year round to 21 was coming out at costs of about 5,700. Now we've done this on complicated modelling. If you dropped your temperature of your house down to 20 degrees, we would calculate your saving would be about 28%. Following that same graph down, if you dropped it down to 19 degrees, it drops it down to 40%. If you drop your house down to 18, it saves 60, down to 17, it saves 68. And if you took your house all the way down to a chilly 16, you would knock 78% off your heating bills. Now, I'm not suggesting we all have our houses at 16, but if you're lucky enough to have a house that you're going away for a long period of time, turn all your thermostats down to 16. If you're lucky enough to have a house with rooms you don't regularly use or spare bedrooms, close the door and turn those down to 16. It makes a really big improvement. You could try and as a family have a green day, and we're going to run the house at 19 for a week, or buy each other jumpers and slippers and save 40% of the energy bill for that week. I've gone on to the slide with PVs. I don't know if you can see that one, Alison, which is they've got the two buildings on. In this slide, which I apologize you can't see, with the two green buildings. There we go, that's the slide there. So this is an office, but it tries to show the impact of PV. Building on the left is identical to building on the right, apart from it's got PV on the south-facing facades. What we were basically looking at doing is running those buildings each year with the photovoltaic tickets, and overall that was bringing the building down by about 40%, which we can see on the next slide. Sorry, not 40%, 20%, I beg your pardon. So basically, heating and cooling that office block all year round with VRF, heating and cooling, or, as you can see there, almost 20% reduction in carbon emissions by just the PVs being on the roof, and we're using all of the cells, which is why I am pro. Every house in this country should have PV on it. Every office block should have PV on it, provided we can get a south or a southwest facing roof that isn't going to have too much shading from other trees or from other buildings. We are then able to feed our plant at source, so it cuts down the energy of all of that. And to be quite frank, if every house in this country changed over to air source heat pumps, we won't be able to power this grid because we haven't got enough energy in this country. And consequently, if everybody starts adding their cars to it, we'll be mounting all the transformers. So we kind of all need to self-generate and try and become mini generations. So we go on to our first example on the next slide. This kind of shows some of the things that we've learned. We're not fallible ourselves. This is an old 400-year-old grade 2 listed house. The client was absolutely pro on being carbon neutral and being in the family for the next generation. It's been in their house for 400 years. So we did a lot of modeling, a lot of restrictions with the architect, not wanting to change radiators, even want to leave the old cast iron in. So they went to the doctor to be cleaned out, repainted, and which really drove us down the line of having to use 70-degree water. Our calculations showed to the client that this was prior to all the energy spikes, that we were going to spend about £8,000 a year on heating and hot water for this house, because the COPs at -5 were down at 2.2. Overall, about 3.4, 3.5. So just on the verge of being efficient. And, it was really touch and go, but the drive was to save carbon, not have costs. Obviously now this house has had all this work, it's all finished, and the bills are quite high and much higher than our predictions because energy's gone up so much. So we've had a lot of live modeling on here about how to close down many parts of this house which aren't in use down to 16 and reduce the temperature generally. And we've seen some really big savings on the on the electrical energy consumption by turning down the heat loss. Obviously looking at how we can reduce hot water loads on this house. And I say I don't think we've got any planners on the call, but the plan for this house to be carbon neutral was to have one of the fields this house is associated with half of it full of PV. Excuse me. That was rejected at planning, and so we're not carbon neutral, and we are going to now appeal with a much more robust, cost of energy. We really do need to make this house planning. So, planners, if you want to save this country, you've got to let more PV go on all these buildings. Enough of my soapbox. Next slide, please. I'm slightly running out of time. I think I'm going to gloss over this slide. Basically, there's a office building in London we did here. We insulated the walls. and we added another story in there, made it very efficient with PV cells on the roof, VRF heating and cooling, LED lighting, and created a very, very high-end EPC A-rated building inside a very old structure. If we go to the last bit of slide, my crystal ball glazing, again, not quite as glamorous slide as Trevor gave us. Where do I think we're going to go? Our national grid is going to get a lot cleaner. Our reliance on fossil fuels is reducing, and with much more use of wind and solar and battery, I think large parts of the summer we didn't actually use any gas the last few years, so it's only going to keep increasing. I think it's therefore important that the government remove the carbon tax that's on our electrical energy, because if it becomes greener, then why are we paying a tax? And that carbon tax, I think, needs to be moved across to gas to make gas dearer. Gas is the polluter and electrical energy is becoming cleaner. Therefore, we've got to avoid this big disparity between the cost of gas against the cost of electricity, and that can only happen with carbon taxes. The government is insistent upon us all using heat pumps to be on our road to carbon neutral by 50. So we've kind of got to get used to heat pumps and accept they aren't as good as gas boilers. They have their challenges. The days of heating and providing hot water with cheap gas for our buildings are now over, and we all need to either accept higher bills or make it cheaper by using less. And with that, I shall jump over to questions.
Thank you. So thank you, Trevor, and thank you, Simon. We do have a couple of questions in the Q&A. I'll do them in order. The first one was, could the pipes go in the bottom of a trench fill foundation? Presume that was on the...
There's an answer for the engineer and an answer for the building control man there, I think. Simon, do you want to lead on, and then I'll chip in on building control implications?
So you possibly could put them in the foundations of your buildings, but your foundations wouldn't be long enough. Typically for a building, you need 200 or 300 meters of linear trench. And then I would be kind of worried that you're putting the weight of your building on my precious pipework, and if it splits the pipework, you've got a leak. And to repair it would be incredibly, well, you'd abandon it. So I think probably not. You can put them in piles because piles are going down, so I guess there's less stress. But not, I would say not in RAF foundation.
And no problem about the concrete enrobing the pipework, so that you didn't get the heat exchange.
I think you need to put the pipes further down. They need to be 1.5 meters down, which is probably below your foundation anyway.
Which is the problem, because then you've got field ground on top of the foundation, and so there's lots of technical issues we'd have to look into. And I'd be a bit concerned, certainly in clay soils, if you're suddenly sucking all the heat out and then maybe you're reversing it and putting heat back in the summer. The temperature differentials might affect the I don't know, volume changes, freezing of the clay, anything like that. We'd have to look at the science on that. But it's not a crazy idea, but it sounds like it's not feasible because of the scale of the foundation.
Yeah.
But yeah, interesting question.
Thank you. The next one, do you recommend running the heating continuously all day or at set times on a thermostat? This one.
That's yours, Simon.
Yeah, normally I would say we would try to warm the building up, then switch it off. However, we have been doing some modelling on a house where we brought the temperature down to 40 degrees, and this house is an old house. It's not got the best thermal values, so it loses its heat relatively quickly, and we are running that 24/7. But we've also got the benefit of this low evening old economy 7 type tariff, where they're paying less than half of the electricity. So they are much more in favour of having their heat pump working hard at night for half the cost to heat the house right up to temperature, and obviously heat all the hot water. So in theory, if you run it all the time at the lower temperature, it's running at its optimum efficiency, but all the time it's running. And I think it really depends on the thermal inertia of your house. But if you get it down to the 40 degrees, then I think it's possible. Yeah.
And just to chip in on that, I think you see heat pump systems that they scrap the thermostat altogether and just work it on weather compensation and get good efficiencies from that. So is that a... Do you think
that is exactly what we're doing at Sarah Hall? Is we're going to look at weather compensation where because we're running at 70 degrees and that inefficient temperature, we're going to have a weather compensator that the outside temperature rises, we'll drop that temperature down on some quite complicated maths so that the temperature of the hot water will drop to provide the necessary heat for those spaces, which will probably mean that we end up running those heat pumps longer, but at lower temperatures. So yes, weather compensation is definitely the next level of controls to save more energy on the heat pumps.
We've got a couple of people asking about flats. How's it going to work in flats? Can landlords be encouraged to utilise things like PV and heat pumps?
No. I think flats are going to be a big challenge. And we've been looking at some very, very high-end flats in London where money is almost no object. And what we're probably looking at doing there is changing the large central gas boilers and putting in large central heat pumps, run hot water around the common parts, and then have a heat exchange manifold at each flat so that you can then charge them for energy. And on another one where the pipework's so old and ingrained inside the buildings, it's really a problem to change. We're just swapping out heat pumps for air source heat pumps with a weather compensator. We'd top up the temperature if you need to in the cold days. And one of the things they're doing is they're changing all the windows because they're old and knackered. So there's a lot less heat loss in those buildings now. And we're hoping then it doesn't need to be at high temperature as much. But that's a possibility on central systems. If you've got a small little flat that's 64 square meters and you haven't got any outside balcony, it's a real challenge because I need a double cupboard, which you've got to give me the space for, and I need a space outside. So I still think there will be a possible smaller market for hydrogen or for gas continuing, quite frankly.
Okay, thank you.
I'd say that certainly landlords, they're not as interested about cost efficiency. They're not paying the bills. So the only way they're going to swap out a boiler is if they're forced to, isn't it? Or if it's cost effective. And
the MEES regulations may offer the protection where, in the MEES regulations, you shouldn't be renting flats with, at the moment it would be EPCD. Yeah. It's creeping up to C, and by 2030 it's going to be B. And if the calculations follow the trail we think they are, in theory, gas boilers in flats won't meet B, and therefore they will be forced to change it to allow them to let it.
There you go. That's a very good answer then. Yeah, that's probably the answer.
I'm going to finish it off there. We're past 5 o'clock. We do have some more questions in the chat and in the Q&A, so we'll get that back to those people on email, from Simon and Trevor. So big thank you to Simon and Trevor for a fascinating topic this afternoon. I hope you've both learned something new and maybe we've changed your perspective on one of those items, hopefully. A CPD certificate will be sent directly to your inbox, so watch out for those. You do have to download it. There's a big green button and you press download to get that certificate. So watch out for that. Our next CPD is on the 17th of April, and we will have a round table looking at the new roles of principal designer and principal contractor. So do subscribe and you will get your invite straight into your inbox. That's all from us. Wish you a good evening. Thank you.
Yeah, thanks all. Thanks for joining us. See you again soon.